Questions, I'll go ahead and get this started, recording. And we'll say, here's what we had for spherical coordinates. We said instead of identifying each point by dropping a perpendicular to the three axes and calling the point at which it intersected on the number line, x, y, and z, we can make an ordered triple rho theta phi, where rho is the distance the point was from the origin. Theta was the same thing we had in cylindrical coordinates. You drop a perpendicular to the xy plane and go back to the origin and the angle in standard position. It's called theta in the xy plane. And then phi is the angle from the z-axis down to this line segment out to the point. So we said in other disciplines, sometimes they like to make this one phi and this one theta, or they like to make this one r, unfortunately. And some of them like to make phi the angle up or down, sort of the latitude. Rather than the arc cosine. This one is nice for mathematicians. We said it's the way it is in almost all math books. The math books tend to write this instead of what I wrote here. So you'll see it in your textbook. Instead of that equation, they'll write cosine. Oops, I wrote this backwards. Phi. This should have said phi equals arc cosine z over rho. I wrote z again. Instead of writing it this way, the book will say cosine phi equals z over rho. They'll say that because they want you to go figure it out on the unit circle. But I like to put it the other way because phi is always between 180 degrees, which is what the arc cosine gives. This always works. You don't have to figure out a quadrant for arc cosine. You just run it in your calculator. Now, we also had equations going the other way, right? We said that rho x, we derived these last time. I won't rewrite them. Rho cosine theta sine phi. Y is rho sine theta sine phi. Then z is rho cosine phi. So these will get you from spherical pointed to rectangular. These will get you from rectangular to spherical, where you could put square root x squared plus y squared plus z squared down here. So it's all x, y, z on this side. But I think once you've computed rho, it's easier just to do this. So I've written it that way. So let's try the example then in spherical coordinates, just a simple one. These are of great value for things like gravity or charged particles sitting out there where you have a radial symmetry to the field it generates. Suppose we did this one. Convert from spherical coordinates to rectangular coordinates. The point 6 pi over 3 pi over 4. So this is the radial distance, the angle, and the angle. We always put these in the order rho, then theta, then phi. Like we put x, then y, then z. So that's my three coordinates here. In order to find rectangular coordinates, it's easy. You just plug it in and run with it. There's nothing more to it than a computer. All right, x equals 6 cosine pi over 3 sine pi over 4, right? Rho cosine theta sine t. Y is 6 sine pi over 3 sine pi over 4. And z is rho cosine phi pi over 4. So you just put them in, and then you have to be able to figure these things in trigonometry. This will make you real good at your trig. You can figure these on the unit circle. Since these are acute angles, I can do something even easier. I can just use the special triangles, right? Here's a right triangle. Maybe that's the 30, 60, 90. So these sides are a half, square root 3 over 2, and 1 for a pi over 3 angle here. Well, I can say cosine is this over this is a half. Then I draw the other triangle from trigonometry, the 45, 45, 90. Say these sides are 1, square root 2 over 2, and square root 2 over 2. We're getting some noise in here. Let's see if I can. I hope that fixed it. Can you still hear me? I hope. Now, sine power 4 then is opposite over hypotenuse is square root 2 over 2. Maybe you have these memorized, I hope. So 6 times sine power 3 is opposite over hypotenuse is square root 3 over 2. And then you expect it to simplify these, right? So let's see, 6 over 2 is 3. I've got 3 square root 2 over 2 on this one. Oh, I've got room to write it, right? 3 square root 2 over 2 is the first one. And then the second one, 6 square root 3, 6 divided by 2 is 3, times square root 6 over 2. That's the second one. And then this one looks like it's 3 square root 2. So there's your 3 coordinates. You write the order triple, right? 3 square root 2 over 2, 3 square root 6 over 2, 3 square root 2. There's the answer to that one. Okay. Well, let's go back the other way then. Suppose I want to convert from rectangular to spherical. That's the hard one. But again, the only hard thing is the theta. The other two are just plug it in and see what it is, really. A little trigonometry and finding phi, maybe. Let's try. Let's convert. Convert this to spherical coordinates. Now it's a little harder, but not much. Rho is just straightforward. You just compute it. It's the root sum square of these, right? Minus square root 3 over 2 squared, plus 3 halves squared, plus negative 1 squared. And you figure that out. Let's see, this is 3/4. This is 9/4. That makes 13/4. This is 1. So I've got what, 17/4? No, wait a minute. 3/4 and 9/4 is 12/4, and 4/4 is 16/4. Try to 16/4 is 2. Right? So this is 2. It's a quick problem. And now tangent theta, that's the hard one. It has to be y over x. It's 3 halves over minus square root 3 over 2. And the trick on finding theta, I do want you to find this exactly. By the way, on the test, I'm going to ask you to show your work. So make sure you can do this. Don't just put it in a calculator or something. The 2's are denominators. I can cancel them. So this is minus 3 over square root 3. Then to figure out what the angle is exactly, provided it comes from a special angle, I can divide both these numbers by their root sum squared. It's square root of minus 3 squared plus square root 3 squared. Right? Is square root of 9 plus 3 square root of 12 is 2 square root 3. Right? So I'll divide top and bottom by that number and get minus 3 over 2 square root 3 over square root 3 over 2 square root 3. And on the top, I get square root 3 over 2. And at the bottom, I get 1/2. What happens when you divide by the root sum square is you make these coordinates y, x on the unit circle. Right? Now this squared plus this squared will be equal to 1 if you divide through by the root sum square. So this will be a point on the unit circle. It might be that this is the y coordinate sine theta, and this is the x coordinate of the unit circle cosine theta. But there's one more choice it could be, right? It might be minus over minus. Now you might think minus this y plus square root over minus a half. But it's one of those two. This might be sine and this might be. Which one is it? Trick is to go back to the original point and say this point has x negative and y positive. It's in quadrant 2. Now, if you're clever and have a good calculator, or you maybe do it online on Symbol Lab or something, you can get an exact answer for that angle just by taking the arc tangent, except it might be in the wrong quadrant. Remember, opposite angles have the same tangent? Opposite angles with opposite terminal rays. If this is supposed to be in quadrant 2, where y is positive and x is negative, then I want this one. This one's in quadrant 4. That's the wrong one. So it's this one. If the sine of theta is square root 3/2 and the cosine is minus a half, I can figure that out in the unit circle, right? I take cosine to minus a half, sine is square root 3/2. We have here somewhere. I get this point in the unit circle. And there is the terminal ray for my angle. What angle is that? Pretty easy, right? I drop this perpendicular as a half length this side and square root 3/2 length this side. So it must be a 60-degree angle, pi over 3. I infer then that the angle in standard position is 2 pi over 3. So we add up to 180 degrees pi. And we'll say, pi theta is 2 pi over 3. So theta is the hard one. Write it in the quotient, divide by the root sum square, and figure the quadrant. You can always get theta. If it's a special triangle, you find the special angle. If not, you always just take the arc tangent and put it and add 180 degrees if it's not the right quadrant. Now, finally, phi is the arc cosine, but I'm going to solve it by the book's formula. It's cosine phi equals z over rho. All right. Well, let's see. Z is -1, and rho is 2. And now you're asking what angle has cosine equal -1/2? Again, I can run to the unit circle. Or maybe it's this angle we just did, right? If I put -1/2 here as the x coordinate for the angle, phi this time. That's one possibility. The other possibility is just down here, right? Which one should it be? Well, remember, it's always between 0 and 180 degrees. It has to be this one. Phi is 2 pi over 3 also. If you were to take the arc cosine on your calculator, it would give you 2 pi over 3, not this one, which is 4 pi over 3. It gives you the one between 0 and 180 degrees. Any questions on that? I don't think it's too clever, but it's mostly plug and chug except for finding theta. All right, this will be the last section for the test again if you just got on.
Hey, sir.
Yeah.
Do you think you can move the screen down just a tiny bit because the
Yeah.
name bar is kind of blocking? Yeah, that's perfect. Thank you.
Okay. Yeah, sorry about that. Tell me when that happens. Can you see this angle phi I wrote? Is that all that?
Yes, sir. Yeah.
Okay, so you make cosine phi equals -1/2. You want the x coordinate unit circle to be -1/2, which means the angle has to turn to here. It's got 1/2 on this side and a unit circle. This must be a 30, 60, 90 triangle. For this is a 60-degree angle. This must be 120 or 2 pi over 3. That's what we're saying there. All right, now the other trick you can do with these things is converting equations. Here's an example. Convert this one to a spherical. X squared plus, let's say 2x squared plus 2y squared plus 2z squared equals 18. And let's restrict z greater than or equal to 0. This is like one of your weather sign problems, actually. How can I convert that to spherical? I mean, z greater than or equal to 0 is rho cosine phi bigger than or equal to 0. What does that mean? I mean, You can do it. There are some easy ways to do this and some hard ways. Let me show you the hard way. One way that always works is to just plug in what the conversion formulas are, right? So you can say this is 2 times rho cosine theta sine phi squared plus 2 times rho sine theta sine phi squared plus 2 rho cosine phi squared equals 18. And that is an equation of spherical coordinates just by plugging in. But you want to simplify this, and a lot of these things, especially with the quadratic surfaces and cylinders, they come out have simple equations, so you expect these to reduce. They amazingly, you think maybe they have arc cosines in them or something, but the quadratic surfaces come out with pretty nice equations, reasonably nice, in spherical and cylindrical coordinates. So I'll write this again, being rather naive here, as rho squared cosine, let's see, sine squared phi, let's put that one first, times cosine squared. That'll be this one. Well, this is this. But now I notice a lot of the same stuff is here, right? 2 times rho squared times sine squared phi, this same term, but now multiplying sine squared theta. So this times this is this term. And if I break out the common factor here, I notice that I have something nice, cosine squared plus sine squared. Let me write this one down. This is just 1, right, by the Pythagorean identity of trigonometry. I've got 2 rho squared sine phi, sine squared phi, excuse me. Plus, this has a 2 rho squared in it too now. 2 rho squared times cosine squared. That's all equal to. Once again, now sine squared plus cosine squared of phi is 1. And I've just got 2 rho squared equals 18. Divide by 2. Oops, what equals? Why do you do these things without thinking what you're doing? Equivalent to. This is rho squared equals 9. All right. Now that's nice, but you can do better because we know that rho is supposed to be greater than or equal to 0. We can square root both sides and say, well, really, this is rho equals 3. It's as simple as that. Now, question, what kind of thing was this originally in rectangular coordinates? What equations does that look like? They look familiar, right? I divide through by 2, we'll see it's in this form. X minus x zero squared. We wrote this down, didn't do any examples because I assume you've seen them in the house, but x minus x zero squared plus y minus y zero squared plus c minus c zero squared equals r squared is the equation for a sphere, right? Appreciate it, circle but we mentioned it here. This is a sphere at x and y zero radius. That's what this is. If you divide through by 2, it's x squared plus y squared plus z squared equals 9 is a sphere of radius 3 at the origin because you subtracted nothing in here, right? So you recognize this is actually a sphere at the origin. And now what does z greater or equal to 0 do? Look how much easier this is if you can visualize it. It's the top half of the sphere. It's what we call a hemisphere, right? So it's the hemisphere of radius 3 that this equation is for. That might give you a hint, some intuition how to do this without doing so much work. What could you do instead? I did this because some of the problems you have to do at least some of this. I wanted you to see, even though this is not how much work you want to do on this one. How could I have done that easier? When you're converting coordinates, you just use the equations that go the particular direction. But when you're converting equations, you can use both sets of conversions. And sometimes one is easier than the other. So if I have 2 x squared plus y squared plus z squared equals 18, I'll factor out a 2 and write 2x squared plus y squared plus z squared equals 18, factoring out that 2. And I recognize rho is the square root of this. This must be rho squared. So I get immediately rho squared equals 9, or rho equals 3. It's not a whole lot easier than doing all this trigonometry. So you can use your equations and replace x, y, and z. That always works, but sometimes there's a lot of work, and it's easier just to use the other set of equations. You can use whichever you want, whatever you want. Okay? There is one more thing to do here. How do I incorporate z greater than or equal to 0 into this? Well, you could figure it out. You can write rho cosine phi greater than or equal to 0, and rho is always positive. Here's a hard way to do this one. Rho cosine phi greater than or equal to 0, but rho is always positive unless you're at the origin. And we're not at the origin, it's a hemisphere. So this is rho, this is cosine phi greater than or equal to 0, where phi is an angle between 0 and pi. Well, how do you make an angle between 0 and pi greater than or equal to 0? You restrict it to the first quadrant. That says phi is between 0 and pi over 2. Make the cosine. That's the hard way. The easy way is to use intuition and say, even easier than this, you say, wait a minute, these are all the points at a distance 3 from the center. That's just rho equals 3, since rho is the distance from the center. So actually, if you're clever, you can just go straight to the answer and say, since it's a sphere, its equation is rho equals 3. That's why we call it spherical coordinates, is because rho equals a constant gives you a sphere of radius, whatever rho is. And here now, when you get this greater than or equal to 0, you might say, well, it means this will pass the xy plane. That's 90 degrees. So you could just immediately say, well, a sphere is rho equals a constant because it's spherical coordinates. And then phi between 0 and pi over 2 at a right angle restricts it to the top half of the sphere. Here's how to do that kind of thing. The hard way, what sometimes you need for some of the other problems, there's just not an easy way. But if it's a sphere, then recognize spherical coordinates will make this easy. You might ask, well, what if we hold some of the other variables constant? In cylindrical coordinates, if you hold r constant, you put r equals a constant. What do you get at r equals 2? What do you get in cylindrical coordinates? Yes? Cylindrical coordinates ought to get a cylinder, right? R equals 2 means you have a circle based on the plane because it's square root x squared plus y squared. And then z is arbitrary. So you slide it like this. R equals a constant, cylindrical coordinates is a cylinder. Rho equals constant, spherical coordinates is a sphere. And so it's kind of a nice intuition you want to have from these coordinates. You might ask also, what is phi equal a constant then? Not as pretty, but you ought to know what it is. Let's put some notes on here for spherical coordinates. Rho equals r is a sphere of radius r. All points at a distance r from the origin by its definition. Theta equals a constant theta 0. Well, if you imagine it, again, intuition is key in this. A lot of times that's the way the mathematicians work. There's a famous quote by Gauss said something I have my results, I just have yet to find out how to get there. Something like that he said. I can't remember quite. But that's the way they work. They have a good intuition and know which direction to move. If, in mathematics, you can be wandering around in the dark hoping to find your keys that you dropped. But I should know which, where to look for them, which direction you dropped them. It's taking a lot of time. All right. So theta equals theta 0. What's that? Think about it. Theta is the angle in the xy plane, and maybe this is the angle theta 0. If I keep a constant theta 0 and let rho and phi be anything, then rho I can go anywhere out, arbitrarily far out. Phi I can go all the way around from here to here, and rho goes arbitrarily far out. So what I get actually is a half plane. That angle theta 0 from the z-axis in standard position there. But it's this half plane that you get when you put theta equals constant. So rho equals a constant is a sphere of radius r. Theta equals a constant is a half plane at that angle. And then how about phi equals a constant? That's really interesting. This tells you something useful for later on. Phi equals some number phi 0. If you think about it, you got all points you come down an angle phi 0 from the z-axis. And then you can let theta go all the way around and rho go all the way out. You get a half cone, right? It goes out forever. But it's a half cone. top half. Well, top half of theta is between 0 and pi over 2. If theta equals pi over 2, it's actually the plane. So it's the xy plane if phi equals pi over 2, because it takes you down the xy plane and go arbitrary direction, arbitrarily far out. Right? But otherwise, it's a half cone. Up here, if theta is acute, phi is acute. Down here, if phi is obtuse, right? But that's nice to know. When you want to write equations in some coordinate system, spherical coordinates is ideal because it's just the equation for the half cone is rho equals a constant, right? That makes a real easy surface equation. It's just like y equals constant. It's a real easy function of rectangular coordinates. Right? So there's some good intuition. And theta equals a constant in cylindrical coordinates. It's the same half plane. It's the same theta. You already know what z equals constant is, right? It's a horizontal plane. So those are all the holding coordinates constant. What do you get? Kind of questions that are real great intuition for solving this problem. All right. Now let's do another equation. We also said we want to be able to do cylinders, not just quadratic surfaces. Suppose I gave you this one. This is number 15 on the homework, probably with different numbers than you have. Suppose you want to find an equation, rho as a function of theta and phi. The reason they do this is that for applications, typically it's easiest to write rho as a function of theta and phi. That's what happens in practice. Like for the sphere you saw, rho equals a constant. It doesn't have to be this way, but hardly ever does anybody need rho and theta as a function of phi, for example. What you need is rho as a function of the other variables. So they're just getting you ready for applications here. If in spherical coordinates, for the surface given by x squared minus y squared equals 81. Again, intuition is real helpful on this. If you can guess what kind of a surface this is in three-dimensional space, then you have a lot of a head start. You know which direction to go again, right? When I talk about Gauss, he's called the Prince of Mathematics. They had his picture on the Deutschmark in the early 20th century, I think. He was so famous. He's sometimes considered, he's one of the three greatest mathematicians of all time, maybe the greatest. He's real fun to read about him. Your book has some of his histories. 2 or 3 years old, he catches a mistake in his father's math calculation. And he said he could do rudimentary mathematics before he could speak, I think. Anyway, something like that. Pretty amazing guy. So I take his advice strongly. How about this one? Rho x squared minus y squared equals 81. Well, sometimes you just don't know what else to do because this doesn't look like rho squared, or if you see y over x, you could replace it with tangent theta, right? If you see rho cosine phi, you could replace it with z immediately. If you see x squared plus y squared plus z squared, you replace it with rho squared, that kind of thing. But I don't see those equations there. So I'll just go back to the basic way that took a long time before and replace x with rho cosine theta sine phi. Replace y with rho sine theta sine phi. Excuse me. That's all equal to 81. And again, we said intuition is key here. What should this look like? We know it. If we divide this through by 81, we get x squared over 81 minus y squared over 81 equals 1. We know that's a hyperbola in the xy plane, right? With a equals 9 and b equals 9. So in the plane, it looks like this. Opens about the x-axis, starts at the vertex 9, 0, and minus 9, 0. Those are the two vertices. Now it looks like that and has asymptotes y equals plus or minus x. So we could sketch this in the xy plane. But wait a minute, it's in 3 space, right? So in 3 space, to extrude it, you imagine z is arbitrary. And so you have a hyperbolic cylinder. You do the same thing in the xy plane that I just drew. At minus 9 and 9 vertices. But you slide it up along the z direction. to make it look like a cylinder that goes up and down forever. So that's what we're actually trying to find equations for. That doesn't look like rho equals a constant or anything, right? So as long as I'm thinking this way, it's just as good as any, right? But it's trying to write rho as a function of theta and phi, and usually this can be done for these quadratic surfaces. What can I do here? I use the same trick when I tried to simplify before. I see some common terms. Rho squared sine squared phi, rho squared sine squared phi. I'll pull that out of both these terms, rho squared sine squared phi. And this multiplies cosine squared here and minus sine squared here. All equals 81. There it is. Let me get rid of some of this thing. All right. Now cosine squared minus sine squared, what's that? It's a trig identity, right? It's cosine of 2 theta. So this is rho squared sine squared phi times cosine 2 theta by trig identity is 81. I want to solve for rho, so I divide through and I write rho squared equals 81 over sine squared phi cosine 2 theta. And again, rho is positive, so I can take the square root of both sides. I don't need a plus or minus. I'll put rho equals 9 over sine phi square root of cosine 2 theta. I like to write this a little better. 1 over sine is cosecant, so we can write this as 9 cosecant phi, and 1 over cosine 2 theta is secant 2 theta, so we can call this square root of secant 2 theta. I don't know exactly what other sign would said. When I saw it, they converted this one to cosecant, didn't convert cosine to secant. I don't know why they do that, but that's the way they wrote the answer for me. So there's this one done for the numbers I have on cosine. You just have to use these trig identities, and you can solve for rho assuming it's not negative. That's all I want to do on the spherical coordinates, I think, except this. There's one more thing I've got. Once in a great while, you want to convert between cylindrical and spherical, and there's a nice way to do that. We'll make this additional note and say, in that picture we had for spherical coordinates, here was rho, here was phi, right? And this was r in cylindrical coordinates, this base length here. So how can we relate r and b and theta? Evidently it doesn't depend on theta. It's all within this plane. What we can do is drop this perpendicular back to the z-axis. Right, make a right angle there to go with this one. And say this triangle and this one are congruent. So if this is r, this is r. And I notice that sine phi is r over rho, right? All the summarization. Sine phi r over rho. And then that tells me by multiplying by rho that r is actually equal to rho sine phi. This can be a useful relation going between cylindrical and spherical. Theta equals theta in both coordinate systems, so there's nothing to convert here. This helps you get some of the rho and phi stuff out of there sometimes. So suppose I wanted to convert the equation for a sphere to cylindrical. Convert. Here's my rho equals a sphere of radius 2. Here's cylindrical coordinates. I wonder what a sphere looks like in cylindrical coordinates. Can't be better than coordinate equals a constant, but maybe it's not too bad, right? Well, what you can do is rewrite. Well, rewrite this equivalently as rho squared equals 4 by squaring. And then rho squared is, this is the other one, I should have written this one too. R squared plus z squared. What's that? R squared is x squared plus y squared, and z squared added to that then makes x squared plus y squared plus z squared. It's just rho squared. We also have this one. I should put this one down too. On this one, if rho squared is r squared plus z squared, I can convert it quickly. Write r squared plus z squared equals 4. And there is the same sphere written in cylindrical coordinates. It's not too bad. It's no harder than an ellipse equation in rectangular coordinates, right? Or a circle, actually. So you can use these kind of things to help you between the cylindrical and the spherical coordinates. That's it, what I want to do on that section. The rest of the period, I'll do some things that are not going to be on the test next week. We want to do vector value function. And the good news is that this is not a real hard section, and you've seen actually some of it before. And we're doing parametric equations for lines. A lot of this section is just parametric equation for lines and circles, reworked within the concept of vector valued functions. And we'll just say this, in calculus 1, or even in algebra, what is a function? Remember? Just a rule that assigns to each input exactly one output. Input from a given set called the domain, exactly one output from another set called the codomain. Right? But the key is it only assigns exactly one output from that set. It assigns exactly one element from a set called the codomain. To each element of another set called the domain of the function. I learned this stuff. I'll repeat what I learned. If the domain is A and the codomain is B, you can draw a picture like this. You can draw a set A, you can draw a set B, and a black box. The function's a black box. It's a rule that says when you throw in X, the set A in the domain, you can throw in anything from the set you want. It assigns something to each of these. It puts it to another point, Y, over here, and then we say Y equals f of X. Indicate that Y is a result from set B that you get from set. And that's all a rule. A function is. It's a rule that assigns to each X exactly one Y. So we use that in calculus 1 a lot. This section is on vector valued functions. The idea is that you put in a number and you get out a vector. So it's vector valued instead of real valued in calculus 1. Calculus 1, you did real valued functions of real variables. Now we'll do vector valued functions of real variables. So this black box, I don't know if I wrote it on there, was F, the function. Anyway. So now we'll say in that context, a vector valued function is a function R of t given a number and it gives you out a vector. X of t, y of t, z of t. Or it could have, this is in 3D. You can do it in different dimensions. You can do just x and y, make it in 2 dimensions. But a vector valued function is 3D. This is just a rule assigning a vector to each number of input. T in this context is called the parameter. It might have some specific values, the domain of this function. which you're allowed to put in. So let's try this. And this should look familiar. Like I said, this is kind of an easy section. Find a vector valued function, R of t, to sweep out the line that goes through the point in three-dimensional space, 4, minus 1, 0, in the direction 1, 2, minus 4. How about that? The idea is this. R of t sweeps out the line with its terminal point. You put it at the origin. That's the simplest way. And so they do this in the physical sciences, for instance. What I want is the point that goes through 4, minus 1, 0. That's easy. I go for 4 on the x-axis. Then minus 1 in the y direction. And I'm at this point. In general, I can draw a box and put it at the opposite corner of the box, recall, right? But this time it's in the xy plane, so it's just a rectangle. And then it goes in the direction 1, 2, 4. So I go 1, 2, 4, and I have a vector up in that direction. So that's the direction vector at the point. I want to sweep out this line by some vector valued function R of t. And I put this vector symbol on top to indicate the vectors coming out, right? Not just f of t. How do I do it? Remember, we had parametric equations for lines before. We just said that the vector form of this equation, remember the vector parametric form? We just write R of t equals R0 plus t v, where v is the direction vector and R0 is a vector to the point. Right? So if R0 is going to be a vector to the point, just following what we did before, it's the vector 4, minus 1, 0, the same components as the point has coordinates. Then the direction v will be this one, 1, 2, minus 4. All I have to do, this is your A, B, C, if you like, and this is your x0, y0, z0. And you just put these things in. So R of t is the vector 4, minus 1, 0, plus t times 1, 2, minus 4. It's the vector valued function 4 plus t, when you multiply t and add them together. 4 plus t, minus 1 plus 2t, 0 minus 4t. There's R of t, the vector valued function. Here it is, R of t. That sweeps out this line as described. What's important about these lines is that they're simple, right? It's like the ancient Greeks. What you really want to pull out of this section most of all is equations for lines and circles. You notice here it's just a at plus b, ct plus d, et plus f, linear functions to each one. That means whenever you see that, you can immediately figure out what's being swept out. If I go the other direction, just for 30 seconds here, and say, similarly, sketch the graph swept out by this R of t. R of t equals 2 plus t, 3 minus t, 4t. What's the graph of that? The idea, again, is you've got a vector. That's not R of t. This was v. I'm sorry, I wrote this wrong. R of t goes to the points of the line. The idea is here's R of some number, t0. Here's R of another number. Here's R of another number. And as t evolves, you move along the points of the line, just like we did before. So R of t is a vector at the origin. This one here, if you just look at it, this is the line because it's at plus b, ct plus d, et plus f, 3 linear functions. You know immediately it's a line. The numbers are a point it goes through, 2, 3, 0, and a number multiplying t give you the direction. 1, minus 1, 4. There it is. So I can know how to sketch that readily. I'll leave that off because we're out of time. This vector value stuff will not be on the test. have that due after the test. If you look, I moved it back. I think it's due Thursday now. All right. See you next time. Bring some good questions for the exam. Thank you for coming in today. Have a good weekend.